Conservation laws to solve a problem. Because at the end of the day, you're using these conservation laws to come up with results that are meaningful for design, for, for looking at operating conditions for a system. Because you have the responsibility to tell your boss that, no, you can't do this, but you can do this. Let me show you the results. Okay? So even though you are using a tool, but this tool can be as powerful as you want them to be. Right? So you go out there, you are going to be the so-called the CFD specialist at the end of the day. Right? So I think that focusing a bit of the theoretical is good. We are not going really in depth. I'm not going to tell you about sometimes how to really derive the whole momentum equation or whatever. But I give you enough knowledge so that you go out and study the basics. Okay? It's all about the basics. So if you look at week 3 onwards, is basically a lot of the theoretical stuff, right, on the topics. But on the practical side, you can see that there are tutorials, projects that will help you to learn the software. So the course has been designed in such a way that it's sort of trying to strike a balance between practical and theory. Okay? All right. Now, next week, I'm going to teach you how to use CFX and Fluent. I'll be here. I'll be guiding you how to set up a problem. So there's no excuse at the end of the day to say that I didn't teach you how to use the software. Okay? I can teach you step 1, step 2 to step 10, how to set up a problem, solve it, and get the results within 5 to 10 minutes. Okay? So even though you are going to your labs today to use the software, but at least you can see what is the layout of the software. You can follow the steps, and when you come back next week, I'm trying to enrich you with other parts of the software itself. Okay, so you get a bonus, at the end of the day. Okay, so if you look at through all the weeks and whatever it is, Anthony will be guiding you on mass and momentum, kinematics, boundary condition is me. Now, turbulence is always my pet area that I talk about, and I can tell you one thing for sure, it's going to come out in the exams. See, I'm already telling you already. Turbulence will be one of the questions coming out in the exams. And it constitutes 50 marks of the exam. So if you come to my lectures, you will get the 50 marks. Okay? I'm very straightforward. All right? I can tell you that among all the students who attended the lectures and who really put in their hard work, they get full marks for their exams. Okay? So it's 50 marks there. So basically, it's 25 marks in your pocket because it's halfway for the exams. Right? And if you come to all the lectures on method, solution, and that constitute part of your exam question as well. So that's what I'm just saying is that this course itself is hard in the sense that you got to put in a lot of work, but the things you get out is actually be quite beneficial to you. So it can actually boost your WAMP a lot. Okay, I'm not trying to fail you from this course. I want you to do well and to put in the hard work, and you will do well. Okay, so I want majority of you to get 90 marks if I can, but you got to put in the work. Okay, I can't do that. You have to put in the work. So, as part of the requirement, I wrote with my colleagues already 3 editions of the CFD book. So this is edition 3. As part of as part of trying to encourage you to actually do well in the course, the top student of this course will get a book from me, a signed copy, right? A signed copy from me itself, right? It's an edition 3. So the edition 3 just came out last year. Now, what is the difference between the edition 3 compared to the 2 editions? This edition is actually, we covered a lot of mesh generation, which is sort of a bit of a lacking in a lot of the CFD books. Now, the design of this book, as you can say, a practical approach. So I really wrote along with my co-authors to make CFD practical to you. So it's very simple to understand, simple to use. Okay? So as an incentive For you guys, okay, the top student of this course will get a signed copy from me. Okay, so I hope that will drive you even more. There are other books as well, so they are more complementary to that. So there are other CFD books are more theoretical based, right? You will find that, but the way we're written is actually more, more user friendly. So this is the assessments. Okay, we have 2 tutorial style problems, okay, which is more on the theory side of things. Okay, so the first tutorial is about equations. The second tutorial is about turbulence, right? In actual fact, if you put the hard work, the 10% is free to you. Okay? So the 10% is actually quite straightforward. To me, it's a bonus to you. So you already got 10% in your pocket if you do the work. Now, the more challenging part of this course itself is the group project and the individual project. That's where the crunch really comes, because you can see that it constitutes almost 40% of your practical work of the course. Okay? Now, and then the final exams is 50%. Group project. Okay? Now, this has gone through a lot of refinement, a lot of actually feedback from students from past years as well. And we are constantly improving the group projects themselves. To talk about group projects, you can read whatever the aims is, but I would like Anthony to share you about actually how the mechanism or how they actually group you into suitable groups to carry out the projects. Okay?
Just a few minutes, a quick word.
This one?
No, I don't.
Yeah.
Because I only prepare one slide, so I don't think I need to present it on the screen. Oops, thank you, Guan. So basically, we will help you to allocate you guys to a group for a maximum people of 5. And then there will be 2 CFD case study, and it will be randomly distributed to each group. So to avoid, groups having the same projects. So basically the 2 projects, one being the flow over an arm body, is just purely based on the meshing techniques, and you need to focus on perfecting your mesh for that case. And the other one is more challenging in terms of theory. It's a counterflow heat exchanger, so you need to deal with heat as well at the same time as the flow, but it won't demand as much in terms of meshing. So I sort of make those 2 topics around the same difficulty. And aside from just allocating you guys into group, you will have your demonstrator to help you out during the tutorial sessions. So this year I want to change the tutorial section such that you won't be just focusing on the group project. Because last year we allocate the whole section for you to meet with your tutors. So you guys just work on the group project, ignoring the tutorial problems in the lab. So this year what we do is for the first 45 minutes, you will be working on your set problems. So every week there is a CFD problem you need to solve, so you won't miss that out. And for the second half of the tutorial, which is 1 hour and 15 minutes, each group will have 15 minutes to meet your corresponding tutors. So there are 3 sections, so 203 and 204 for 2 to 4 p.m. There will be around 60 students in each labs. And there will be around 12 groups, and each of the groups will meet your tutors in 15 minutes to discuss with your tutors what's your finding and let them know your progress, and they will consult you whether you are behind or whether you are doing well. So basically that's how it works. So there shouldn't be any complaints that you are not, having the opportunity to express your ideas or raise the question or your concerns to our demonstrators. And okay, so the group allocation and your corresponding demonstrator will be announced in week 2. So it will be happening very soon. I believe Chang has already worked out your allocation, and we will announce it. But if you have any concerns about your group, you need to come to us at an earlier stage, because group project is due on week 8. That's very soon. So any changes you need to announce to us before week 3, I think. Okay, so that's pretty much from me. I'll hand it back to Guan.
Okay, so what is the purpose of having this group project itself? So we've been, Anthony and I, we've been discussing a lot for the past few years of how this course itself. We believe that the group projects can be beneficial to all of you, because we hope that you work together, right, to produce something. Okay, that's the first aim. The second aim is that what we have found in the past years as well is that it can give you an insight of how to write a report as well. So you can use this knowledge itself for your future use when you go out to industry writing a CFD report. You know, what does the report should entail? What needs to be included inside it, okay? So basically, I'll come back to that. So the group project itself, we are going to provide you a template. So the template will sort of have a short literature review, project description. As Anthony has shared, that there's a lot of emphasis on meshing and so forth, which I'll talk a bit more as well, because CFD itself actually do depend a lot on the mesh you use for your problem. So if you get a bad mesh, you get a bad solution, okay? So the meshing becomes a quite integral part as well of your project. And then you have the models that you use to solve the problem. And of course, that will include like what are the boundary conditions, the scheme that you use, the convergence, and the CFD models. And that's just some discussion on the results that you get. Now, that template itself will be given to you. And now what I like to do, I just want to go back to individual project. The mistake I made last year was trying to adopt the same format as the group project. This time, you will be the scapegoat or the guinea pigs of a new incentive I'm trying to do in this individual project. So what I want from this individual project this term from you guys is, how are you going to analyze your results? Okay, so that means that if I give you an XY plot or some color pictures, what do they mean? You know, how are you going to tell your boss at the end of the day, you see this picture, this shows that this is the design conditions, this is how you can operate. And then at the end of the day, your individual will also entails where, why aren't your results comparing with the experimental data? So what are the reasons? You know, you got to think outside the box, outside the realms of your knowledge sometimes, to see why your results cannot compare. So why is there a discrepancy? So I want you to go into deeper to explain, you know, or justify what is the thing. And the thing that I want to link from the lectures is the week 10 lecture, verification and validation. You know, how are you going to verify your results? How are you going to validate your results? Because CFD results, anyone can produce a CFD result because they are just color pictures at the end of the day, right? Okay, you guys can go out there, use a software, give me a very nice picture. At the end of the day, I'll throw back, if it is a wrong picture, I'll just throw it back to you anyway, because I know by experience that doesn't make sense, right? So you got to make sense of the pictures that you produce and how you analyze. So this is the target at the moment. The individual project, we have bumped up the marks. Last year was 15% to 20%, which I find that, okay, this is my experience. What I found is that last year, people just put the results and just said, figure 1 shows this, figure 2 shows this. There's nothing analysis of it, you know? So I thought that this is not what the individual project is all about. Individual project is about you putting in some work to analyze the results. So I want that from you this year, Okay, it's going to be hard. You're not going to get the 20% easily, but I think that you can ask your demonstrators. Your demonstrators are there to help you, right? And in the middle of the term, we will give you sort of a report template as well, how you should write your report. It's not going to be long, okay? Maximum 5 to 10 pages. That's it. Your figures alone will cover almost majority of the report anyway. So the more results you put in, the more results you can justify, your explanation will be better, okay? All right? So this individual project, we want it to be slightly different, but also to link to the lectures that we are offering this year. And I think that in the past, we have not tried to enforce verification and validation, but this time around, we're going to enforce more verification and validation. So think about it, how you're going to validate and verify your results, okay? Again, set problems will be given to you. So now, the reason why we adopted more of a set problems because we have done the work for you of sourcing experimental data for you to validate. Okay, because the hardest part about validation is sourcing good data. So we have screened through all the literatures and so forth, and we are doing the hard work and present it to you to say that solve this problem based on this experimental data and this geometry. So we've done the hard work for you already. All you need to do is to analyze your results, okay? So you don't need to get the data and so forth. So that's why we thought that setting set problems really save you time a lot, okay? So is it worthwhile doing it? Yes, because it constitutes 40% of your total marks, right? So the whole emphasis about having the group project and the individual project at the end of the day is for you to learn how to not only use the CFD tools, but also how to use it to analyze CFD problems, fluid flow problems, okay? So think about how you're going to solve the problem as well. It will save you a lot of time in the long run, okay? So don't jump into actually solving it immediately. Think about what you're going to do. Think about how you're going to solve it, and it will save you lots of time. Right, so now I really start my lectures. What's the time? 12:21. So what is CFD, or computational fluid dynamics? Okay, let's break down into basic look into fluid dynamics. Anyone has taken fluid dynamics last year? Okay, there's a few. Okay, few. So for those people who know fluid dynamics, you know what is fluid dynamics. It's basically looking at either fluid in dynamic mode or stationary mode. So the fluids can be static or in motion. Okay? So you're basically looking, for example, if you really want to look at something, is trying to study the flow of air in this lecture hall. That's basically what fluid dynamics is all about. Okay? Now, CFD adds another component, which is computational. So what you're doing now is to study the fluid weather in motion using computational tools. So that's basically what CFD is all about. Okay? So that's what we term CFD is all about. People do even associate CFD as colorful fluid dynamics, okay, because we can produce colorful pictures as well. But more importantly is to study fluid dynamics using computational approaches, right? Now, CFD is very, very, very closely linked, okay, to mathematical equations. So that's why Anthony will be spending in week 3 looking at the fundamental equations based on the conservation laws of mass, momentum, and energy, right? So that is very closely linked because without those 3 laws, you basically don't have fluid dynamics and you basically don't have CFD, right? So that's why it's important that you are, that you know all these fundamental laws. So basically, let me see what I've done. Okay. So basically, I can tell you that the fundamental laws is mass, momentum, and energy. So what is a conservation law of mass? Anybody knows?
Mass is neither created or destroyed.
That's right. You can't create new mass, and you can't destroy the mass. So that means that you take, for example, of this lecture hall itself. If you have an air supply from a duct, right, there must be the same air taken out from this room itself. So that means that if you have 100 kilograms per second coming in, you must have 100 kilograms per second going out. There's nothing can be created in the middle, okay? Mass conservation, right? And you can see from even the computational approach itself, you can even check your mass error. Your mass error has got to be very, very small because you cannot create more mass. You create more mass, it means there's something wrong with your solutions. Okay, that's something to check as well. Right, what is, anybody knows the fundamental law of conservation of momentum? Anybody? Yeah, sort of same. But what is the, who is the person that actually look at conservation of momentum? Huh? Newton? Okay, it's about Newton's second law. What is Newton's second law? Huh? What is Newton's second law? Come on, you should know this. For those people who do mechanics, you know what is Newton's second law.
Someone got it.
What is it? F is equal to ma? Yes. So force is equal to mass of the fluid times the acceleration of the fluid element. That's basically Newton's second law. Okay? Anthony will describe to you how we actually derive mathematical equation base equals to F equals to ma. Okay? Now, what is conservation of energy? Very similar to mass as well. Yeah, so basically it's the first law of thermodynamics. Okay, for those people who does heat transfer, you should know the first law of thermodynamics. So you can see that CFD itself is nothing really foreign. These are all the things you have learned throughout your mechanical course, right? Like the conservation of mass, conservation of momentum. All we are doing here is to translate the laws into fundamental transport equations for a fluid element. Okay? Simple as that. Okay? Now, as Anthony says, is that meshing is actually an integral part of CFD. It is true. Because if you get a good mesh, then you can minimize your errors down the track. Okay? Getting a mesh is important. And I would say that getting a mesh is also an art. So that's why I put the word art, right? It is not something which I can say that this is definitively how you should do meshing. Because every problem is different. Every fluid dynamics problem you're going to solve in practice, okay, it will be different. But there are certain guidelines we can provide to you to get a good mesh for what you want to solve. Okay, I can provide you the guidelines. Anthony can provide you the guidelines. All the demonstrators can give you the guidelines as well. But we can't say that, yeah, that is the mesh you should use. We can never say that. Okay? Right? But what we can say is that if you use a specific mesh to resolve the important parts of the flow, you will get a really reasonable or good solution. Okay? If you resolve the flow of interest of the problem, you will definitely get the good solution. That's what we can say definitively. That's why we talk about fine grids, fine meshes, concentrating your mesh to the flow regions of interest. Okay? Right? Now, mesh also is also very tightly linked to validation and verification. So you can see that, you know, whatever you're going to do in group project will be fed into your individual project as well. Because you need to look at your solution to be mesh independent. So that means that the more resolve your mesh, you shouldn't have a change in your prediction. So that means that you achieve a mesh independent solution, which is important. Okay? So basically for your assignment, you need to at least to make, at least for the group project itself, to have 2 meshes to compare, preferably 3. So we usually denote it as coarse, medium, fine. Okay? So what it means is that the more you resolve your problem, especially when your fine mesh comes, the solutions from the medium mesh is not much different from the fine mesh. So that means you achieve mesh-independent solutions, which is important. Okay? So what are the different type of meshing that you can have? Now, the first figure I'm showing here is a transonic flow over an aerofoil. Look at this mesh itself. You see that there's a lot of mesh around the aerofoil. Why is it so? Anybody? What details? Pressure difference, one thing. More? Some more. For those who are aerodynamics people, why is it so important to have mesh around the aerofoil? Velocity difference. So what is the term? There's two words there. I want you to get to. It starts BL. Boundary layer. Exactly. It's to resolve the boundary layer. Why you need to resolve the boundary layer? Because the velocity changes dramatically from the wall above from the aerofoil. True? So that's why you have a lot of mesh around the aerofoil. Why is it there's a lot of mesh beyond the aerofoil? Any hints? No? Yeah, not so much. For people for aerodynamics, what is the key thing you want to look at for transonic flow? SW? Shock waves, right? Is to predict the shock wave. That's where everybody from the aerodynamics industry is looking. Where is your location of your shock waves, right? And that's why you see there's a lot of mesh beyond the tip of your aerofoil. Now, if you look at this aerofoil itself, the meshing seems to be a bit regular. So we call it structured meshing. That means, what you mean by structured meshing is more of like a rectangular type of meshing, right? And there is a purpose, because a rectangular type of mesh, it tends to be so-called more accurate than other type of meshing we are going to show you later. So basically, this is another example of a structured meshing. Again, it's more rectangular type for a projectile. So that's a bullet, okay? Again, the same principle applies where you got mesh around the projectile itself to resolve the boundary layer, and also very fine mesh beyond at the back of the projectile to predict the shock waves, okay? Right? So why is this structured meshing is important? Effectively, structured meshing gives you more accurate results in principle. I'm not saying that it is a hard fact, but in principle, it gives you more, a better result at the end in terms of accuracy. But sometimes it's just not possible to use structured meshing because the geometry of the domain is so deformed, you have to use alternatives. So what are the alternatives? The other alternative is unstructured meshing, which is basically called triangular meshing. Now, triangular meshes tend to able to conform to your design of your system, of your geometry, much easier. But tetrahedral meshing, or you call triangular meshing, sometimes you are unable to control the density. Okay? In terms of density, you tend to use less element in structured meshing compared to tetrahedral meshing. To achieve the same accuracy, you tend to have to use almost 2 times or 3 times more elements compared to structured meshing. So that means that to have a good, if you want to compare apples to apples, you may use, let's say, 500,000 elements in comparison to 1.5 million for a triangular mesh. So that is the accuracy you have to think about. When you start thinking about that, you start thinking about computational run time. So because with a 500,000 mesh, you get faster solution and more accurate than 1.5 million. But sometimes you have to do a compromise. Okay? Like what you see here is a compromise. You can see that around, so this is part of the, I think, the solar car, okay, design itself. If you look at near the tip of it, okay, near the tip of that, you still have a bit of structured meshing, right? You don't have triangular meshing. Why is it so? because the prismatic meshing is more suitable to resolve the boundary layer at the end of the day, right? So that's why you have a mixed meshing at the end of the day. But beyond that, I can just do a triangular mesh if I don't really much concerned about what is the characteristic of the flow there. If I'm more concerned what is the flow around the body itself. Now, this is another type of meshing. Okay, it's called polyhedral meshing. Now, to tell you how accurate is polyhedral means that it's like a honeycomb meshing. You're talking about five side elements or 6 side elements. Polyhedral is in between sort of rectangular and triangular, somewhere in between, right? So polyhedral gives you the flexibility of conforming to very complex geometries, but also it gives you a reasonable accuracy and also a reduction in number of elements to mesh your geometry as well. Okay? Now, polyhedral features is in Fluent, but it's not in CFX. Okay? So what this Fluent does is that it takes a triangular mesh and combine a polyhedral with 6 triangular elements. So you can see that from one polyhedral element, you have a reduction of even 6 already. So basically think of this. So basically what it takes is that it takes the 6 triangles and reduces it. So you can just imagine that, that a triangular mesh can be reduced using polyhedral mesh. Now, for a pure polyhedral meshing generator, you have to use another code called *CCM+. Unfortunately, you're not going to be using that code because we don't usually use it in our teaching. But just to give you a sense that there are a lot of CFD codes around, but even though we just focus on CFX and Fluent, which is predominantly used by a lot of people, there are other codes that are as good as these codes as well. So I just want to put it out there and tell you that there are other codes that actually will give you better features and better use out of this. So for unstructured meshing itself, you can have different types of meshing. This is what you so-called the cut cell meshing, where you can see now the mesh actually do not need to align with the other meshes, which the software itself allows you to do a lot of, like innovative interpolation to get the results. Okay, that means that it's basically like an overlaying mesh on top of a background mesh itself. Okay, there's one strategy. So basically, if you look at this, for example, if you want to resolve the flow along the body of this car itself, you basically can so-called use like an overlaying mesh or embedded grid inside. Okay? So there are other features as well for this type of meshing. You talk about, so the software you're going to use is up to you how you want to learn, the extensive use of the meshing. This is really up to you. Okay, what we're going to provide to you in the set problems are actually very simple problems, but you can use that for anything you want to use. So it's really, up to you how you want to use the code. Okay, so these are just some examples of meshing. So let me give you a bit of I guess in a guideline or some hints, for meshing. If possible, use structured meshing because you can see that the inflation layer that I showed you for some of the examples is where you need to resolve the boundary layer. Especially for boundary layer, it's always better to use structured meshing. Okay? As I said before, put the mesh where you think the flow gradients will be strongest. So that means that if you look at for the aerofoil problem, where your velocity is at 0 at the aerofoil surface, it will dramatically increase to the free stream flow. So that's where you put the most mesh there. Okay? Your mesh should look smooth. That's important. So what I mean by mesh is look smooth is that if you do want to have an irregular mesh with non-uniform spacing, that means that the ratio of the preceding mesh should not be greater than 2. So that means that if you have this size, you try to limit between 1 to 2. So basically, this will be 1.5, again 1.5. It's got to be smooth. You can't have a mesh of this size and eventually have this mesh size. That is not smooth because at the end of the day, you got too much of a step change of the flow, and you will find that your solution will diverge very easily. So having a smooth mesh is an important part, okay, to have a good solution as well, right? Most important thing, okay, especially when you start looking at complex geometries, always check your mesh for negative volumes. Because if you don't check your solution and you're getting a solution, the solution may be very far off. Even though it runs, you get a solution and you look at this and, oh, it looks okay, but it could be wrong. So that's why CFD is not a so-called a straightforward process. It's always, you need to do it more iteratively. That means that you got to run the solution, check your solution, validate. If it is good, you know, you still need to do a few tests iteratively to get to where you want. Okay, it's a more of an iterative process. So this is a framework that is in my book, which I think it really highlights what CFD is all about. So CFD basically can be, you know, for a CFD analysis, not the code itself. The analysis framework involves the preprocessor, the solver, and the postprocessor. Next week, I'm going to deal with the preprocessor. That means that I'm going to use the software to demonstrate to you how to create a very simple geometry, to mesh it, to put the material properties, for example, to solve for water or air, let's say in a dart problem. To set the boundary condition means that what is the velocities you want to set for laminar or turbulent, right? And to basically use some of the default models and then solve the problem and present you results, okay, within 1.5 hours, okay? Now, nowadays computers are quite fast, so I'm not going to solve a very complex problem, but just to demonstrate to you that computers have advanced a lot, and we can actually now demonstrate CFD during real time as well, okay? This is to see how much CFD has advanced. Now, from week 3 onwards, we basically talk about the solver. So that's why I'm just saying is that when you start playing or using the CFD course, it is good to appreciate at the end of the day what these tools are all about or where they have come from. They basically come from fundamental transport equation of mass, momentum, and energy. And I said that if you know this fundamental basis, solving any type of problems is easy, okay? It's very easy. I tell you, even from this point, the conservation equation has 4 terms. The first term on the, okay, let's say the equation on the left-hand side is a time term and the convection term. On the right-hand side is the diffusion term and the source term. 4 terms. These 4 terms makes you solve anything you want to solve. Mass, momentum, energy. For combustion problems will be the mass fractions and anything you want. Okay? So I'm just saying, I'm putting to the point where CFD is not as complex as you think it is. Okay? If you remember these 4 terms, even you don't know what equation, you remember these 4 terms, and you can see the physics of these 4 terms, okay, I'm happy. So let's take, for example, momentum equation. You have your time term. Okay, time term means that if the flow is time dependent. If the flow is steady, the time term disappears, right? So there's no time term. So now you got your advection term equals to the diffusion and the source. For a flow in a pipe, what drives the flow? Pressure. Pressure difference, right? Pressure difference appears in the source term. dP over whatever, right? dP over whatever distance, right? It is the pressure that's going to drive the flow, right? What governs then laminar or turbulent? Huh? Reynolds number. What is the definition of Reynolds number? It's a ratio of? No, inertia over viscous. Okay? So if the viscous is dominant, your Reynolds number is low. So let's say 100 or 200, right? If your inertia is high, that means that your Reynolds number will be very large, okay? So the inertia and the viscous effect is actually linked to the advection term and the diffusion term. So that means that for laminar flow, your diffusion term dominates over the advection term, and vice versa for the turbulence. So what drives the flow at the end of the day is your source term. If you've got a high pressure gradient, that will drive the flow more, and you get more inertia, and you have a certain characteristic of turbulent flow. All right? So this is where I'm coming from. The equations that I'm telling you at the end of the day has physical meaning. Okay? They are not equations that I'm going to show to you that has no meaning. It's all driven by physical meaning of what the fluid flow is all about. See? So if I explain to you, it's so easy, right? Right? It's not hard. So don't be overwhelmed when you see equations in week 3. Right? Yes, there's a lot of partial differential equations. Yes, there's a lot of vector symbols or whatever. But just hold back and let Anthony explain to you in simple terms what equations are all about. Because when you understand that, you will just feel that, oh, I know this stuff, no problem. Okay? And when that knowledge comes to turbulence, when I start deriving the equations, you will see that that knowledge will become even very simple when you derive turbulence equations themselves. Okay? I will teach you step by step. Okay? I can tell you that derivation of turbulence equations would be in the exam. Okay? Write it down. Derivation of turbulence equation would be in the exams. And it constitutes major of the marks. If you do tutorial 2, in this course, you will get the full marks in your exams. Okay, that's a direct link. Okay, because I will just tell you, just look at tutorial number 2, and it will be in the exams. It will be in a similar form. I can ask you in a different way, but it will be exactly what it is. Okay, no surprises. Right? If you do tutorial 2, your exams is sorted out. Okay? So, as I said before, that the solver actually part of it is the equations. Another part of it is the solver settings. Now, why are we concerned with solver settings? The problem, Blaine, is that the conservation equations that you derive cannot be solved analytically. You can't solve that analytically. You have to solve using some numerical methods. That's what the crux of all CFD codes is all about. Okay, it's the numerical methods. Okay, we are not going to tell you what are, to try to describe you all the numerical methods for the CFD code system, but we can give you some basic background what methods to solve the problem. So what they have done is that they take the equations, convert it to algebraic equations, and then use numerical solvers to solve this equation, right? But in solving the numerical equations, you have to solve it iteratively. That means that you have to do iteration. So CFD is about convergence of the iterative process. That's why we have to monitor the solution, and then we have to determine then whether the solution is good enough, or how the convergence is determined by what you set out in your mesh. So everything is linked. Okay? It all links back to your meshing and also what your results you get at the end of the day. Okay? And we hope that we can impart this knowledge second half of this course itself. Okay? Right? So you will learn, convergence even today, how you solve a backward-facing step problem, how you look at the solution converging and so forth. You learn it today, even today itself. But treat it as a face value at the moment. We will get into more details as the course progresses. Okay? So, I talked about this already. You'll be there in week 3. Boundary conditions. Now, boundary conditions are as important as equations that you use. Why? Because if you don't put or don't impose a correct boundary conditions, whatever results you get today is all garbage anyway, right? So boundary conditions are still an integral part. So to set a proper boundary condition is important, okay? So what also I'd like to cover in this course is to look at the boundary condition even from a physical point of view. You may need to do some modification of your geometry to set the boundary condition. So boundary condition mathematically has a certain, certain format or certain feature, which you cannot always mimic the real physical boundary condition. But you can modify your geometry to get to where you want to mimic the real physics. Okay, this is something I will talk about when I talk about boundary condition in week 5. Okay, so this was my PhD supervisor. He always tells me things. Guan, giggle. Okay, if you have giggle, you garbage in, you always have garbage out. Right, that's for sure. Okay, so boundary condition is very, very important. So turbulence. Now, why are we concerned about turbulence? Why so much hoo-ha or basically trying to understand turbulence? Almost all industrial problems or engine problems are turbulent. Why? Because we are dealing with high Reynolds number flows, unfortunately. Even the airflow in this room is turbulent. Okay? So turbulence is as important, and we need to know how to solve turbulent flow in a CFD context, right? For flows in laminar regime, we can even describe from the equations, but more complex flows need to be solved numerically using turbulence. Today itself, you may actually encounter turbulence default model K epsilon or whatever. I will talk about it later, as the weeks go by for turbulence. But just accept it at the moment that you are using a good model, for your current problem. Discretization. I talk about, CFD equations converting to algebraic equations and so forth. So the transformation of the equation to algebraic equation is via discretization. So that means that, take, for example, this room itself. What you try to do here is to take this geometry of this room, divide it into small elements. That's what I demonstrated here. And within this small element itself is where you have all the algebraic equation of the conservation laws. That is that you solve the mass. Let's say, for example, you solve the mass, momentum, and energy for each of the elements. And from each of the element itself, you start to march to adjacent element and consider adjacent element to effectively solve the flow throughout this room itself. Okay? You understand that? Okay? So that's why I say that CFD is very dependent on meshing. Why? Because appropriate meshing will give you the appropriate prediction. Why? Because each of these elements you put in the meshing solves the conservation laws. So if you can resolve your flow of interest using a good meshing, you will get a good result. So discretization, again, forms the reason why we are using CFD. Okay? Again, so we will talk about week 9 for discretization. Week 8, so in week 8, we're going to look at post-processing. So looking at what type of beautiful pictures you can produce. So there are beautiful pictures you can produce like using XY graphs, contours. I'll show you some examples there. Velocity vectors and others. And again, we look at solving week 9. And week 10 will be verification and validation. So this is an overview of solution procedure that you monitor your solution for doing a CFD calculation. So this is an analysis of results. So this is looking at flow over an obstacle. So you have the front of the building, let's say the rear building, right? And this picture shows the flow impacting the front of the building, and then you have a flow separation as it climbs up the wall and it flows over it. Depending on how fast the flow actually hits the building and then deflects, the recirculation region would increase, right? And this was actually generated using a streamline approach. You look at the colors here, the colors indicate the pressure impact by the wind itself or the velocity. So you can see that with one picture, I can tell you actually what it says. It says a lot of things. It shows the flow. The colors indicate perhaps the highest and lowest velocity. The pressure, the contours on the building, on the obstacle itself shows you the pressure. See, right? So this is how you should tell. Okay, at the rear of the building, as expected, you will see that for like a backward-facing step, you have the flow flowing here, you have a recirculation region beside. Why? Because the flow separates away from the build at high flows. Okay, so you have your old recirculation region at low velocity, and you can see that the color blue here actually indicate low velocity as well. So you can see that the pictures itself do describe you all the physics that you require. And basically this flow will reattach itself to the main flow somewhere behind the rear of the building. Okay? XY plots are very important. Now, let's look at this one itself. Usually what happens here is that if you put a uniform velocity here, let's say this is flow over a channel, right? The flow, because there's friction there, will try to slow down the flow near the walls because of the boundary layer. And eventually what you see is that the flow in the middle has more freedom to move, will move faster. And eventually it will develop to a parabolic profile for laminar flow. Okay? For turbulent flow, what do you think will happen? What is the profile going to look like? The answer is there. What do you think in turbulent flow will look like for a profile? Somebody said, yes, it will look like. Why? Because you got bulk of the flow moving as quick as possible, right? It'll be flatter, right? So this is one of the characteristics of turbulent flow as in comparison to laminar flow in a channel, okay? Right? Now, because, okay, let's talk about now turbulent flow and laminar flow. Laminar flow, as I said before, you look at the Reynolds number, the viscous effect is more dominant than the inertial effect. So what does the viscous effect does? What does it do? Physically. I see somebody deep in thought. The viscous effect diffuses the flow. Okay? It disperses the flow. Okay? That's what the viscous is all about. So that's why when you disperse the flow, when you have diffusion, that's why it starts to diffuse. So it basically diffuses. Okay? Right? That's why laminar flow is predominantly dominated by the viscous effect. The inertial effect, because if you have a high velocity, the velocity moves quicker. Okay? Right? So that's why the diffusion is not as dominant. So that's why you have a flatter profile at the end of the day at the outlet. Okay? Because your inertia takes so much dominance, it just kills the diffusion. Right? So in this instance, you can see the conservation of momentum equation already. That's why I talk about time, advection equals to diffusion and Sostom. Okay? You know the physical things of what is dominant in the equations already. Right? Okay? Right? So the top part is to look at the velocity profile over an obstacle. So basically what you see, the velocity drops for this figure itself. Then it goes up, and then basically you have a lot of the recirculation behind the obstacle itself. Okay, verification and validation have distinct definitions. You will know this in week 10, but I'll bring it up to you to sort of give you the definition. Okay, I've already uploaded this lecture into Moodle, so you can look at the definition. But I'm trying to describe it in a very simple way. Okay, let me do it this way. Validation is easy. Validation means that you take experimental data of a certain flow, you're trying to compare your numerical results against your experimental data profile. It's very straightforward. Verification is slightly more complex. Okay? So my understanding of verification is to make sure that whatever settings you put for your problem, you basically assess like mesh converge. a bit of mesh convergence as well, mesh independent solution, your meshing and so forth. So in terms of CFD, your verification is more on basically how you set up your problem, make sure you set up the proper boundary condition, assess it against different convergence criteria and so forth. Also test different numerical discretizations and so forth. Okay, I should be awake by now. Was I sleeping? Nah. That was the same alarm I hear at 6:20 every day in the morning. So validation is more like assessment of models. So for example, when you solve turbulent flow, unfortunately there's no fundamental equation for turbulence. Okay? You have to use turbulence models. Okay? By the word definition, models means that you have to make sure that it's damn bloody hot. Yeah, see? You should remind me. So when validation means that when you have a numerical model to assess, you need to compare with some experimental to see whether how good the model performs. Okay? So that is the purpose of validation. Right. Now we come to the interesting part. So what are the examples of CFD? Everybody knows that CFD has been used a lot in automotive engineering. Okay, this is one example of a NASCAR example. Two NASCARs flowing each other, and they want to see actually what is the flow separation behind the red car affecting the blue car itself. Okay, because it will actually involve in the design of their, of their wing behind the cars and so forth. So this is one classic example. CFD has been used a lot in the automotive engineering. In F1, they use CFD a lot. I'm pretty sure Red Bull uses a lot of CFD as well, okay, because they have the money to actually spend to actually improve the performance of F1 cars, okay? Everybody knows that, right? Automotive engineering again. Now, this is another interesting area where CFD has been used quite extensively as well. So this is the CT scan of your trachea as well as of your nose. Okay, if you're wondering what it is. Okay, it's basically what we have done is that I work with my colleague from RMIT, and we're actually trying to look at nasal, inhalation through your nose system. So what we have done is that we actually did a CT scan of this for nasal sprays, and we look at the particle deposition of nasal sprays using actual real geometry of a human nasal. Okay? And this is another one. We look at the branches to the lungs. So basically, this is the main bronchial tree geometry to see how much of the deposition of the nasal as you go through the lung itself. So this is another application itself where CFD has been used quite extensively in the biomedical science and engineering. This is looking at blood flow, if you know what it is. Okay. So this is a typical flow behavior in a bifurcation of artery. So what we wanted to see is that if you look at this artery itself, there's a basically sort of a blockage, a narrowing of that. So it's a very important part of trying to understand the blood flow, through the artery. So what happened here is that if you have blood suffocating here, basically your plug suffocating here, then the flow will be more predominantly on that side. You want to see the effect itself. So this is another work we've done with one of my research fellows. We look at different artery sizes. So basically there's arterial and artery. You can see at the end of the day, the flow is actually very different. The flow itself in the artery is more chaotic when you compare to flow in the arterial or the capillary. Okay? Okay, another example that if any of you get a chance, this was done in conjunction with Professor Jun Wang from our mechanical building. He is looking at using how to use abrasive jet for cutting materials. So basically it's a high-speed airflow with particles, microparticles itself. So what he did, what he wanted me to try to understand the flow dynamics of particles injecting from the wall itself. But at the end of the day, what we wanted to see is where should we put the sample away from the nozzle to get the perfect cutting. So we did a CFD analysis on this. Okay, you can see it's a polyhedral mesh. What I'd like to show to you, okay, is we look at different shape of particles. This is spherical. This is sort of a triangle by fusing three spherical. You can see that the so-called triangular particles, I'll do it again, has a narrow spread. So that means that the triangular particles will be able to basically cut the material more efficiently. Instead of that, because you can see that that is so spread, you will get a particle cutting at irregular parts of the materials. Okay? So this is what CFD can do as well. It can give you an animation. Okay? It can actually animate things and look from a more, from a more movie-like type of results. Now, this is the type of work we've been carrying out in our research group as well. We've been looking at nanoparticles as well as microparticles. So this is one example of how you can use CFD to actually look at the aggregation of nanoparticles. Why is it important? Because firstly, we want to see the self-organization of these particles, and secondly, to determine the structures for some other purpose as well. So this is nanoparticles. This is microparticles, where we demonstrate that if we look at particles agglomerate, what it tends to do is that it moves away from the bulk flow and sticks to the wall itself. Okay? So this is the physics that we can understand using CFD. Okay? Another example is what we have done is how to subject nanoparticles to magnetic field. Now, this was carried out one of my PhD students. So what we can do is that based on the aggregation of ion particles at nano size, we can align the nanoparticles according to the direction of the magnetic field. Okay? And this is one example of actually a shear flow where we impose a velocity in this direction, a velocity in the opposite direction. And basically, you can see now the behavior when we subject to the magnetic particles is trying to jiggle around, dance around, and try to counteract against the shear flow. Okay? And you can see the particles are moving left and right depending on the flow. So this is for very low velocity. Okay? And this is for higher velocity. Okay? You can see now the flow now is really moving. So we basically have a repetitive walk. So the particles going here is feeding back. But basically, because of the shear flow is again trying to go against the magnetic field. And this is typical type of behavior in, let's say, in MR dampers for, for buildings and so forth. So, yes?
What are the units?
Oh, the units are the time, sorry. Okay. Is it the time? No, the units are how many particles tend to stick to each other. So basically, the red one says that there are 4 or 9 particles sticking to that particle itself. I'm very sorry. Okay? So you can see now the flow is now getting, the particles are sticking more, and you can actually affecting the flow as well. Okay? Right. Okay, this is another example of, again, even though it's a very simple problem, but there's actually a lot of development behind this. This was developed by one of my PhD students looking at how to track a bubble in a stationary fluid. It sounds so boring, but he spent 6 years developing this. All right? But the good thing about this is that what he has done, okay, now let me tell you the good thing. He put a surface mesh on the bubble, but using the minimal CFD mesh. So it's called a front tracking method. And the good thing about his method is that he's getting exactly what you see in experiments. Okay, that's how fantastic it is. So if you look at a 1 milliliter bubble, right, and we know that it's going to stay spherical, and it stays spherical. Okay? The different colors you see is the different surfaces cutting the control volume of the background mesh. That's why you see different colors. If you look at a 2.5 millimeter bubble, do you think it's going to be deformed? Yes, no, maybe. It's going to be deformed? It stays spherical or deformed? Huh? Elongated. I'll see. Let's see. is going to turn to an ellipsoid. Okay? So you can see that the front and the bottom is a bit squashed. It's becoming more of an ellipsoid at the end of the day. Right? For 2.5 mils. Okay? Now, for this one, 5 milliliter bubble, you can see it's becoming a cap bubble. Okay? So what happened here is that for a 5 milliliter, because the surface tension is not as high as a 1 milliliter, 2.5 millimeter, you will see the bottom surface moving faster than the top itself. So that's why it's becoming like a cap bubble, okay, at the end of the day. For a 10 millimeter bubble, it's very interesting that you see now the bottom surface is moving faster, and then what you see that there's a penetration of the fluid towards the middle. You can see soon. See? And what happened here is that eventually the surface moves so fast it breaks the bubble. Okay? The penetration is so strong.
I was just wondering, did your student also model the breaking?
No, impossible at the moment. Do you want to do a PhD with me? I will definitely give that project to you if you can model that. I have another student working on this, looking at heat transfer. That means he's looking at condensation and evaporation of bubbles, you know, and he's getting very good results as well. Yeah. So if you want to do a CFD, great. Right. As I said before, fire engineering is one of our strengths as well in our research group as well. So this is my PhD student as well, who became, you know, I mentor him a lot. And what he has done is he has done marvelous things to my CFD codes. He has put my CFD to another level. You know, I put it this way. I just put it at another level, okay? So basically what happened here is that if you look at a buoyant fire, or maybe you talk about, you know, a campfire, you can see it. What is the physics behind a buoyant fire? Okay, let's talk about this. So if you want to model using CFD, you use a mesh. It could be a rectangular mesh, structured mesh, or unstructured meshing. It involves temperature. Why? Because hot air rises, cold air drops, right? That's how it is, you know? And then you have your density drops because of your temperature, right? And then you have air entraining into the thing to sustain the flaming process, right? The air flows into the campfire, we call it a campfire, to sustain the flaming, right? So basically that entrainment involves convective heat transfer. There's convection involved, there's heat transfer involved, right, using convection. And then also you have radiative heat transfer. Very, very clear. If you stand away from the campfire, you feel the heat. It's due to what? Radiation, right? It's due to the radiation process. And also what you have is the combustion process. Okay, let's put it simply. Fuel plus oxygen gives you combustion products. The fuel comes from the wood sample, for example. It reacts with the oxygen at a suitable temperature, right? So you need an igniter. Once you get a good temperature, it will ignite, it will combust. The air comes in to sustain the flame itself. As it feeds into the flame at the right temperature, it keeps on flaming. As long as your fuel is constantly being supplied to the solid sample above that itself, okay? And during the combustion process, you have combustion products. One of the products that comes out is soot. Okay, soot is basically, if you burn wood, you see black smoke. That is soot. Okay, that is a byproduct of basically the combustion process, right? And basically, that soot is important in fire engineering. Why is it important? Because soot is a radiative particle. Even a micro size is radiative. So for example, if let's say, touch wood, there's a fire in this lecture hall itself. The carpet is burning, right? Let's say at the center of this carpet, you will see now the smoke goes up and forms a layer beneath the ceiling, right? For those people right at the up, they will feel the heat. Why are they feeling the heat? because the smoke layer is radiating the heat due to the soot, right? That also brings to a point is that because of the smoke layer radiating away from the fire source, other materials will start to degrade and eventually they will burn. That's where flame propagation comes in. That's why eventually this whole lecture hall will be engulfed with fire. Okay, it's the mechanisms behind this that is important. So basically what we have done is that we have tried to develop an in-house code to actually look at the Bowen fire. So this is one example that I want to show to you, right? This is a 1 meter squared fire of roughly 1 megawatt or so. So what we're trying to look at the puffing effect. So what happens is the air entrains here, form a bulge, and then it continues to entrain air above there and form a bigger bulge, and then it pumps up. Okay, this is what we can do now with our code, right? And this is a very interesting problem. It was done by him, by the way. Okay, I acknowledge him. So let's say, what is this problem all about? Have you heard about the Quakers nursery home fire? Anyone? You heard? Okay. There were, I think, eventually 11 people, elder died. Okay. That, you know, is due to what? Smoke inhalation. Not so much during the fire. During the fire, what happened here is that there were actually 2 elderly people actually died in this room. Okay. When I say died, basically non-existent. Okay, their bodies were not found because they were incinerated in the room itself. Okay, and you know, if you know the case or what happened is that there was a nurse, right, that lit up the fires in this room. They actually killed 2 people. That's the first thing. But while this room was burning, a lot of smoke was produced, and while evacuating, 9 other elderly people got intoxicated with the fumes from this room and eventually died 1 week after. So it was a very serious event. So what happened here is that the Fire Rescue New South Wales, the firefighters came to us and said, Guan, Anthony, can we try to determine where the fire started? So we were trying to, to get data, where the materials are, and eventually ended up that when we burn in 2 locations, the burning prediction and also how much of the materials burned sort of compared very well. Compared very well to what was being seen, okay, in the post-forensic thing. So let's look at the simulation itself. So what happens is we started the fire in these 2 beds. So there are 4 beds. There's cupboards. There's the door, okay? Now, you see this incident where you have the fire spreading there is basically due to the windows breaking. If the windows has not broken, you wouldn't see the fire propagating right towards the end. It's because the windows broke, there was basically the air, I repeat itself, okay? There was the air coming from the doorway, pushing this fireball right up towards the window. And the fire spreading there starts to burn all this surrounding materials themselves. This was used in the court case, okay, by the firefighters. It sort of add more fuel to actually convict the guy. Okay, this is what called forensic fire engineering is all about. We're trying to do reverse engineering to actually use something good out of it to help the firefighters and the New South Wales police, okay, to actually convict this guy. Okay? Now, this is another problem we are solving as well. Okay, I think Cheng is solving it wrong. It's called a swirling fire. Now, why are we interested in swirling fire? If you look, Australia is a country of bushfires. Okay? And if you look at some of the worst case of bushfire, it's actually due to basically the fire swirling and also the fire, the flame strengthening as well. So what we wanted to understand actually how a swirling fire behaves. So this was one of the experiments carried out by our colleagues at China. And you can see that the fire initially swirls around, and then eventually it will straighten up. when it achieves enough momentum, it will become like a very thin flame itself, right? All right. Chang is still solving this problem to now. Okay, he's getting very good results. Okay, all right. So this is the extent of our fire research and in terms of fire models that we have. Okay, in our group. Right. Next, this is again. Now, everyone you heard about the Glenfell Tower fires, right? All right. You see, it was very disastrous. So what will happen here is that we look at trying to understand why the fire started or how the fire behaves. Okay, we look at actually for this example, we look at the gaps behind the wall and the cladding. Okay, so what we have found that if the air gap was not as big, you actually don't promote the flame spread, to the neighboring rooms itself. So the worst case scenario. Yeah.
You need to go out.
Huh?
Like you can play it here.
Yeah.
Oh no.
Oh, I need to. That's okay. No problem. I can show it to you. I'm pretty sure I have it here, right?
I'm not sure which video it is.
I'm pretty sure I have it here. Maximum, minimum, right? Hey, okay.
Yeah. Max mean 5.
Okay. So that is the best scenario, okay, where what you see is that the fire is contained and it's not spreading outside of the room itself, all right? And for the other case, what we found is that if your air gap is sufficiently large, okay, you will see that the flame actually propagates out and the fire actually promotes through chimney effect, will spread to the other room and actually affected the fire. That actually what happened to Glenfell Tower. So it's a combination of the cladding, which also provide the fuel to burn, but also the chimney effect, okay, that means the air gap itself, starting from the room of fire origin, spreading to the neighboring rooms up the floors themselves. Okay, this is what we can try to understand from a fire engineering perspective. Okay. Right. Now, I'm almost finished. Okay, almost finished. So CFD is even used in power generation itself. So we can even design wind turbines and so forth, or even placements of wind turbine across the terrain of the turbines themselves. And this was a work that we look at, actually looking at the effectiveness of solar panels placing against the wall of a building, right? Now, it is important because we want to cool these solar panels passively. That means there's no additional power or basically electricity to actually generate it. So this is one of the work carried out by one of my PhD students. So this is a flow of a heated wall. And basically what you see, these color pictures here, is a turbulent vortices. Okay, basically the rotating flows of it. This was solved using large eddy simulation, okay, which you can really solve the temporal flow. And all the detail flows can be captured through the CFD simulation. So this is my last slide. Bear this analysis framework in mind throughout whole this course. We're going to do the preprocessor next week. Most importantly, understand how you physically interpret your computational result using your post-processor results. Thank you, and I'll see you in the labs. At 2. Thank you.
How do you switch on the egg?
Yeah. You can switch.
did it with swap or Yanni and Rock.
I know.
It's okay.
It's okay. It's just that when the groups are set, then you can't change anymore.
Yeah.